Welcome to the Explainer. Today, we're diving into a really cool paper that finally decodes the relationship between the two heavyweights of modern AI. You've got attention, the engine that powers models like GPT, and then you've got these powerful new challengers, state space models, or SSMs for short.
So here's how we're going to break it down. We'll start by setting the stage with our two main players. Then we'll introduce what's basically a Rosetta Stone for understanding them both. After that, we'll get into three absolutely game-changing findings from the research. And finally, we'll unpack what this all means for the future of AI. Let's get into it.
All right, so in the world of AI that needs to understand sequences, things like text or audio or even DNA, we've had a long-reigning champion, and now a seriously powerful new contender has stepped into the ring. On one side, you have attention, right? The core mechanism inside transformers. It's incredibly powerful, lets the model see the whole sequence at once, but boy, can it be a beast to compute. On the other side, you've got state space models. These are built on different principles, processing things one step at a time, which makes them insanely efficient. On the surface, they seem like they come from completely different planets. And that brings us to the central mystery, the big question this paper tackles. For years, we've thought of these as totally separate paths. But what if they aren't? What if they're actually deeply, fundamentally connected? To even begin to answer that, the researchers had to get clever. They realized they couldn't compare apples and oranges. They needed to invent a common language, a kind of Rosetta Stone that could describe both architectures in the same terms. And the key to this whole thing is a concept they call the effective interaction operator. Now, don't let the name scare you. Just think of it like a special X-ray machine. It lets you look inside any sequence model, doesn't matter if it's attention or an SSM, and see the exact blueprint for how it lets all its inputs talk to each other. And once you use this X-ray, you see two fundamental patterns emerge. There's the explicit way, which is what attention does, kind of like a big open conference call. And then there's the implicit way, which is how SSMs work, more like a game of telephone following very specific rules. For the first time, we can describe them both using the same language. And now the fun begins. We can finally compare them side by side. So, with this powerful new lens in hand, the researchers made their first bombshell discovery, something they call the interaction rank gap. Okay, so what is interaction rank? It's basically a score for a model's flexibility. It measures just how rich and varied the patterns are that a model can learn to represent. The higher the rank, the more expressive and, at least in theory, the more powerful the model is. And this is where it gets really interesting. Their framework proves, mathematically, that a single head of attention is fundamentally stuck with a low interaction rank. It's constrained. SSMs, on the other hand, they can represent way more complex, high-rank interactions. There's a huge gap in their expressive power. So why is this such a big deal? Well, it means that there are some problems out there that an SSM can theoretically solve, but a single attention head simply can't. It's not a matter of training it longer or with more data. Its very design makes it impossible. This, of course, leads to the second massive revelation, and it's the one that gives the paper its title. Okay, if one attention head is limited, how many do you need to catch up to an SSM? And the researchers didn't just guess or run a few experiments. No. They went and proved it with a formal mathematical theorem. This is not a hunch, it's a fact. They actually call it the equivalence theorem, and it does something amazing. It creates a direct one-to-one mapping between the complexity of an SSM and the number of attention heads you'd need to perfectly mimic it. And the answer is just so beautifully simple. H equals K. If an SSM has an internal dynamic system of complexity K, you need exactly K attention heads to replicate its power. Not one more, not one less. This is it. This is the direct mathematical bridge between these two seemingly alien worlds. All right, let's get to the final, and you could argue the most important finding of all, because it reveals a fundamental trade-off that sits at the very heart of how we design these incredible AI architectures. So this all comes down to how these models actually learn. For a model to remember something from way, way back at the start of a long sequence, the learning signal, what we call the gradient, has to travel all the way back without fading out. And this fading problem? That's called gradient attenuation. Now, this is where attention has a secret superpower. The paper proves that attention has what they call a gradient highway. The learning signal can basically jump across huge distances in the sequence without losing any strength.
This is precisely why it's so darn good at long-range tasks. And that brings us right here to the ultimate trade-off. It's a choice. Attention gets this perfect, lossless memory highway, but each head is limited in its expressivity. SSMs get this incredible, almost limitless expressivity, but they risk that learning signal fading out over really long distances. You can have one, or you can have the other, but it seems you can't have both.
So, after all that, what's the big picture here? What's the key takeaway? How does this actually change the way we think about building the next generation of AI? The most crucial point is that this paper finally gives us the mathematical theory for something that AI architects have kind of been discovering through trial and error. The choice isn't between a good model and a bad one. It's a choice between two very different and very powerful sets of trade-offs.
And this leaves us with one last, really provocative thought. If one model has what amounts to perfect memory and the other has near infinite expressivity, then the future of AI probably isn't about picking a winner. The real challenge, the next frontier, is figuring out how to fuse these two superpowers together. But that is an explainer for another day.